Okay. First thing I noticed is that I spent last night and this morning shortening my talk so it would last 25 minutes. Now I realize I've got 3 minutes more, so I could have went to bed early last night. So I've got 25 minutes to talk about particle accelerators and 50 years of colliders. That means I've got 30 seconds per year. So I have to be very fast. I'll start with Rutherford, who, unlike many of the quotes that you've seen around this auditorium today, said something which was true. Then I move on to 5 decades of colliders, and quite a lot of the CERN people are here today, and some of them will even remember some of these accelerators and colliders we had. Then before going on to the future circular collider, I'll talk about societal applications of particle physics. So Rutherford was the godfather of accelerators. In his inaugural presidential address to the Royal Society in 1928, he said, "I have long hoped for a source of positive particles more energetic than those emitted from natural radioactive substances." And I think this was the start of a long quest for the production of high-energy beams of particles in a very controlled way, as you've been hearing already. Particle accelerators from today, as you've already heard, are among the most complicated and expensive scientific instruments ever built by mankind. And they exploit every aspect of today's cutting-edge technologies and engineering. Now, I'll give you a very simplified sketch of a synchrotron collider. And this was based on the LEP machine, because that's the only slide I had. Basically, a collider, synchrotron collider, consists of clearly a vacuum chamber, usually 2 vacuum chambers, magnets to bend the beams in a circle, magnets to focus the beam the way you want them, accelerating cavities to accelerate the beam, and places where you collide with experimental detectors. And also you need to inject 2 types of beams, and surely to extract them as well. But that's not all there is. There's much, much more than that. There's beam diagnostics, instrumentation, computer control, cooling, powering the magnets, many, many, many others. There's civil engineering, clearly, for the tunnels and so on. So this is the CERN's present accelerator complex, and you can see it is pretty complex. Series of circles, which are synchrotrons, all joined up by lines, which are beam transfer lines. And this whole complex runs to get the LHC operating, starting from the PS, which was built in 1959. There's 2 linacs at the moment and 9 synchrotrons, which tells you what are the most important type of accelerators today because of the high energy. So now I'll move on to the path to higher energy colliders for fundamental research. Now, most people don't even remember this, but the CERN intersecting storage rings operated from 1971 to 1984. And this was actually the first Hadron Collider ever built. Most people thought it wouldn't work. Many people thought it wouldn't work. I came to CERN in 1972 to work on the ISR. And it was, when you look at it today, a very unusual machine. These are 2 of the intersection points. You can see the size of the tunnel, which was huge. And you can see, amazingly, that there's no super detector around the collision points. And that's an important part of what was learned from ISR. ISR was a fantastic place for accelerator physics, but it actually produced no particle physics. And the reason for that was the detectors weren't suited for colliders. So the first thing, which was a legacy of the ISR, was how experimenters can design detectors for colliders. And that's clear from nowadays. Second thing, which was very important, at least for the PP bar, was the observation of what we call Schottky noise and what we call stochastic cooling. There was also a big step forward in the use of collimators, collimation and background control for the experiments. Luminosity calibration by Vandermeer scans, which is still used in the LHC today. And I think this was the birthplace of control of what we call the impedance seen by the beam and the onset of transverse instabilities because of that impedance. So after the ISR, there's what's called the SPP bar S. This is where protons were collided against antiprotons in the SPS. So this was in 1976. Carlo Rubbia, Peter McIntyre, and David Klein proposed to convert one of the high-energy proton accelerators into a proton-antiproton collider. At the time, there was the accelerator, the high-energy accelerator Fermilab, and the other one under construction at CERN, which was the SPS. Now, to do proton-antiproton, you clearly have to have a small beam size for the antiprotons, and to do this, you need to stochastically cool the antiprotons which you generate. And this was the stochastic cooling experiment, which was done in ISR in 1974. And you see the cooling each time the cooling is switched on, and you see the growth of the beam size each time the cooling is switched off. So this was the first time that it was shown that you could actually cool a beam of protons or antiprotons, but most importantly antiprotons. And this was published in 1975 by these gentlemen. Without this, the PP bar could not have been operated. In 1984, Carlo Rubbia and Vandermeer, who proposed the SPP bar S, and Vandermeer, who wrote the paper and invented stochastic cooling, damping, they shared the Nobel Prizes. This is them in CERN celebrating it. The next two machines were SLC, Stanford Linear Collider, and LEP. Stanford Linear Collider was an ingenious linear collider. It used the old 2-mile LINAC at Stanford in California to, first of all, introduce some damping rings to make the emittance or the beam size much smaller, and then have a positron return. And then the electrons and positrons were arranged to arrive at the same time in the SLD detector. And this was really a major breakthrough because it was small. It was very, very complicated. It took a long time to get it working properly. But in the end, that's the way in which we probably would go forward for any E plus E minus colliders or a very, very large tunnel. At the same time as SLC was being developed, we were looking at putting a very large tunnel in the Geneva area. You can't see it. This is the Geneva airport, and this is the Jura Mountains. Now, I think there were 4 variants altogether at this time. This was the beginning of the 80s. The first one was a 22-kilometer circumference tunnel, which would have avoided both the Jura Mountains and the airport and fitted quite well in. And this was actually probably the optimum solution. However, there were 3 other, and you can see them here. There's a red, you probably can see the yellow, and the black. The number 1 was a 30-kilometer machine, which went right through the Jura Mountains. The number 2 was a 26.6, which is the same circumference as what we have now, which passed the Jura Mountains as well and was far away from the Geneva airport. And the third one, which was the one which was actually adopted, was the red trace, which is 26.7 kilometer tunnel, which just went through the Jura Mountains for about 3 kilometers and touched on a tangential to the Geneva airport. Now, it should be said that the 22-kilometer, which used to be called the Blue Book, was the optimum for LEP, but the LHC was already being considered at the time, as has been discussed in the book by the DG at the time, Herwig Schopper. The chosen variant, the red one here, gives the maximum circumference possible between the Geneva airport and the Jura Mountains. But we still went through the Jura Mountains by a small amount, by a few kilometers, in a region called Crozet. And this is the trace of the tunnel. I hope you can see it. It comes around here, and this is the Alps in the background. That's the Lake Geneva airport. Now, this is what happened in the part where we went through the Jura Mountain. It wasn't a very good idea to do that. Maybe the 22-kilometer tunnel would have been much better. We had huge high-pressure water infiltration in the 3 kilometers, which was going through the foothills of the Jura Mountains. And this probably caused a 1.5 years delay in the civil engineering for the tunnel. So now I move on to a short history with Beam at LEP. So 1988, we did an octant test in the summer. '89, we did first turn, first collisions, and so on, and did physics at the end of the year. And for 5 years, from 1990 to 1994, we did the Z0 physics. Remember that we already knew from the SPP bar S what the energies were, so we could set the machine to those. From 1995 onwards, we had the LEP2, which was an upgrade. And this involved the gradual addition of 288 superconducting cavities once per year at the annual shutdown, usually around Christmas time. So we went 65, 80, 92, etc., and ended up in 2000 with energies above 100 GeV. And these energies, we were pushing for those like mad because some people thought the Higgs boson may be there. This shows you in 1999 a typical example of how we increase the voltage per turn. You need this voltage per turn because of synchrotron radiation. And you see that to get to these high energies, we had to have 3,500 megavolts per turn. This is a lot of RF, a lot of... in this machine, there was 20 megawatts of synchrotron radiation being produced at these high energies. So there are a lot of amusing stories associated with LEP. I haven't got time to do them here. I usually concentrate on those because people are more interested in the amusing stories than the physics usually. We had lots of stories affecting the beam energy. We measured tidal forces in a very expensive way. We also could see water level in Lake Geneva being changed, and we had the impact of the fast train from Geneva to Paris, TGV. We also had beer bottles, we had electrocuted deers, and we had sextupole miswirings, and these were affecting the operational efficiency. I have all those slides, but I haven't got time to show them. Now I move on to the Higgs boson, and this was a big question because the question for us was, would the Higgs boson be discovered at LEP, LEP2 actually, because events were seen at 114 GeV in 2000, or would it be discovered in the LHC, or would the Tevatron beat the CERN machines to discovery of the Higgs? And this was a very, very important year. In 2000, the big question around CERN was, should we run LEP2 in 2001 or stop it? And so it was a question of old versus new, the old LEP machine versus the LHC machine, and there were various inputs were saying that LEP, if you ran LEP, it would delay LHC by up to 2, 3, 4 years. And then there was the ever-present competition from the Tevatron. And then in order to make LHC, we needed resources, the manpower resources would needed to be transferred. We also needed the materials budget because the electrical bill from LEP was enormous. So I think for me, this was the first and only civil war I've ever witnessed at CERN. There was no consensus to make a decision, a bit like Brexit nowadays. No consensus in CERN committees. And in the end, the DG made the decision to stop LEP at the end of 2000. And this was a hugely unpopular decision, but as it turned out, the right decision because the Higgs boson wasn't at 114 GeV. So what was the legacy of LEP? Clearly, there was a fantastic amount of very high precision physics came out of it, and that was helped by the luminosity we produced, the energy calibration. I think it's fair to say that LEP is a reference for any future E+ E- ring colliders, such as the ones being proposed, you heard in the first talk by Michael. So the legacy to future colliders for LEP, I think probably a very important thing, and you've seen this for the layout of the FCC, avoid mountains for the tunnel. It's a real difficulty. There was also a lot of experience on running large accelerators because 27 kilometers is not easy. You have to have very, very precise shutdown planning, cold checkouts, and so on. And for the first time, we had real-time feedback on beam parameters, controlling the orbit in real time, controlling the values of tune, which we call it, and controlling instabilities. And we also gained a lot of experience on running large-scale superconducting and cryogenic systems. So following the decision to stop LEP, remember this was at the end of 2000, the beginning of 2001. So the whole of the accelerator team were now focused on the new machine. So we'd given up on LEP. We're now going for the LHC. The first thing we did then, we started a new committee called the LHC Machine Committee, and this was the mission which we had in 2001. LHC Machine Committee is still running now, what, 18 years, 19 years later. And the idea of this committee was to use the experience and expertise gained in LEP to prepare beam commissioning and operation of the LHC. And these were the things which we wanted to do. We wanted to maximize the performance of the injectors. The injectors are the prime parameter which controls the performance, certainly the luminosity of the LHC. We needed to evaluate experience from other accelerators, colliders, and we needed to develop a detailed scenario for commissioning. Very importantly, get special software requirements for commissioning and operation, and also plan machine developments for the upgrade of the machine for the future, to continuous improvement. Here I've given a list of the names of the people who were in that first meeting, and all of them made really high and substantial contributions to the LHC operation during the following years. This started, remember, this was 8 years before we actually started to operate the machine. So I hadn't got time to go through the whole business of the LHC, but I've just given a short history here. Approval was in 1994. Construction was 14 years, from 1995 to 2008, directed by Lynn Evans, who was the project leader. The first beam was in 2008, and the accident was also at the end of 2008. We spent about 16 months with the repair in 2009, and we started up the machine in 2010. It's been running to now. Initially, we started up at 7 TeV, center of mass energy, and 2 years later, we ran at 8 TeV, and after the full repair, because we didn't do the full repair in 2009, after the full repair in long shutdown 1, we're now operating at 13 TeV. So that's the trace again. So the first collision at 7 TeV was on March 2010. Here you see the first events at each of the experiments. This was a really big deal for us because we were struggling to get the machine working, and then we actually see not only does the machine work, but the experiments are all measuring collisions. 2010, first year of running. You remember we started way back here. I said March, and for a long time I think we were very nervous because we were afraid of having another accident, so we were very careful about what we did. We wanted to make sure everything was safe. Towards the end of the year, we began getting a bit more confidence, and this is the luminosity. So this is the number of events you produce as a function of day of the year in 2010. And the number you must remember is 45 inverse picobarns. That's just remember the number 45. In 2011, we produced 6,000 inverse picobarns. So at the end of 2011, we were starting to think maybe we can get the Higgs boson here after all. And this was an estimate of the integrated luminosity, the number of events, plotted as the day of the year in 2012. And this was shown to the experiments at the end of 2011. We also had from the experiments what they thought they needed to get 5 sigma Higgs boson. So we thought September 2012, if there is a Higgs boson, because no one's really sure it was there, then we would either discover it or say it doesn't exist by September 2012. When we started running the machine, the red dots are the actual progression of the rate as a function of time. And on the 4th of July, there was the usual big physics conference, and lo and behold, both experiments announced that they have a 5 sigma signal for the Higgs, CMS and Atlas.
All right, so now we can look at the sensitivities.
The seminar on the discovery of the Higgs.
The ZZ and gamma gamma. This is what we get. They line up extremely well, and in the region of 125 GeV, they combine to give us a combined significance of 5 standard deviations. The last month of running that did it. So I just thank Steve for...
So this is the history of the first 3 years, 45, 60, and in 2012 we accumulated 23,000 inverse picobarns and had the Higgs boson. So this was a really exciting time at CERN. The next year, Francois Englert and Peter Higgs got the Nobel Prize for their theoretical discovery of this mechanism. So now I'll move on to accelerator applications before I go to the FCC. So this is difficult to go into details here because there's so much to say. This is a summary table of the application of particle accelerators. This is from a European Commission report. Now, the areas of interest are medical, industrial, security. You've heard about some of this before, synchrotron light sources, neutron scattering, et cetera, et cetera. Biggest number of accelerators, of course, is used for X-ray radiotherapy, 14,000 linear accelerators in Europe. There's also around 70 proton and carbon machines for treating cancer. And there's also a lot of machines, like 1,600 of them, producing radioisotopes, usually for medical. Industrial, there's a lot of things. There's ion implantation, ion beam analysis, materials processing, sterilization. Probably one of the biggest fields to arise in recent years is synchrotron light sources. Almost every country has its own synchrotron light source, FEL, etc. now. And this number is growing all the time. These are machines which, for the lack of LEP, the synchrotron radiation was a real nuisance because we had to put in more and more cavities to replenish the energy which the synchrotron radiation took out. But then many people realized that the synchrotron light was a very, very useful scientific tool, and now they're doing studies in biology, medicine, materials, material science. I'll not go through the rest of them, but this is a summary table of the operating particle therapy centers in Europe. These are either protons or carbon ions at the moment. There's a lot of work going on for other types of ions, like various types of ions, like helium and so on. This tells you the countries in which they are, and these are fairly expensive machines which are used for better treatment of cancer, if you want, less toxicity with the treatment than there is with X-rays. So there are many particle therapy centers under construction in Europe. This is from 2007, so it may be a little bit out of date, particularly for Manchester here in the Christie Centre. Supposed to start operation in 2018. I think it started at the end of 2018. And you see the countries here, what type of, they're all protons, these, and they're all cyclotrons with the exception of 2 of them, which are synchrotrons. So technological spin-off of particle physics. The most famous one is the World Wide Web. And what many people don't know, the World Wide Web was invented in March 1989. And the reason, the task which Tim Berners-Lee was asked was to find a way to distribute all the data which will come from the LEP collider throughout the universities in the world. And so that's how he discovered the World Wide Web. So he wrote his paper in March '89, and LEP started operating in July 1989. Synchrotron light sources I've already mentioned. That's a big spin-off. We've heard previously cryogenics and superconductivity, MRI scanners. Also, there's a new proposal to use superconducting cables for transfer of electrical power with large power over large distances with much less losses. There's the accelerators for radioisotope production. I think this is very, very important. PET scans I'll come to later. Accelerators for cancer therapy, I've shown some of that. There are other accelerators for things which you would never believe. If you look at this Symmetry magazine from Fermilab, there's a lot of useful information in there. Accelerators are used, as I said, for food sterilization, amazingly diaper production, mining ore analysis, and cancer diagnostics, and also clearly medical imaging. So one of the big questions, I put questions twice up there by accident. So one of the big questions are actually questioning fundamental research. Some people have asked many times during discussions, why spend millions on studying obscure things which have no uses? Or what possible use or application could there be for, say, dark matter, neutrinos, or the Higgs boson? And the only answer which you can give to that is that we never know what's going to be useful until we study it and understand it. And I think we got that in the last slide of the last talk as well. So fundamental research historically has driven disruptive innovation. I think that's irrefutable. However, the path from discovery to application in most cases is totally unpredictable. And I'll give you an example of that, a few examples of it. Antimatter postulated in 1928 and much, much, much later used in positron electron tomography scans, where you basically inject the patient with a positron emitting radioisotope, and that positron interacts with an electron, makes two photons which you detect outside the body, and you can make an image of, for example, learning a new language or cancer, a cancer tumor. Now this is what's used very, very regularly nowadays. So let's start to see how we got to this very unusual diagnostics. We had special relativity, we heard about that before. We had quantum mechanics at the beginning of the 1900s with special relativity. These two together allowed Dirac to postulate the discovery of positrons. Quantum mechanics gave us fundamental chemistry. It gave us transistors, electronics. There was Lawrence who invented the cyclotron around the same time. Fundamental chemistry allowed us organic chemistry synthesis. And the invention of the cyclotrons and the organic chemistry synthesis allowed us to produce positron-emitting isotopes. With electronics, we were able to build faster, cheap computers. Positron-emitting isotopes generated the radiopharmaceutical industry. From quantum mechanics, we had the birth of nuclear and particle physics. And because of this, we developed finely pixelated gamma ray detectors. And when we had fast computers, radiopharmaceuticals with positrons, and finely pixelated detectors, we had positron emission tomography. So I think if you had asked around 1928, would Dirac, Planck, or Einstein ever have imagined these applications of their fundamental research? I think the answer would have been a very sound no, because it's a very complex path before you get to here. The other thing which is interesting to know, the scientists themselves could not foresee the applications. Rutherford was questioned by a journalist about the splitting of the atom, and he replied that the energy produced by the breaking down of the atom is a very poor kind of thing. Anyone who expects a source of power from transformation of these atoms is talking moonshine. And he was obviously wrong. We've heard about Einstein and all the beautiful things he's done, but one of the things which he would never have expected was his time dilation, the bending of the curvature, which was shown a few talks ago, is actually taken into account. The correction for this is taken into account in your GPS system. It's of the order of 30 microseconds, but it would make a 10-meter error after just 5 minutes of travel time. So this is actually an application of relativity. Clearly, Maxwell, with electromagnetism, we all have our little cell phones in our pockets, and these telephones are used electromagnetic waves to communicate. They could never have foreseen what would happen 80 or 90 years later. So now I move on to the FCC. In 2012, when I was still at CERN in the accelerator sector, there were 13 proposals. There was a European strategy group in 2012. The next one was supposed to be 6 years later, last year, but it has been delayed. And we, in the accelerator sector, proposed these 13 different proposals, and they were categorized in these 3 different categories. There are many things here, far too long to go through, but I'll show you there's one for the high energy LHC, there was one for the 80/100 kilometer tunnel, and there was one for what we call LEP3, There was also LHEC in there, just above the LEP3. So this paper was written in preparation for that European strategy group, and it was written in 2012, and the authors are here. The 7 authors are given there. The interesting thing about this was at the end of that, we had a look at the farthest energy frontier. This was 2012, don't forget. And what we said here was a super 100 kilometer ring, a super high energy LHC. The option on the left is strongly preferred. This is what you've seen from Michael Benedict in the first slide. Here you go through the mountains and you didn't want that. Here you go into the lake, Lake Geneva. So if you think of this super high energy LHC and you add on the LEP3, which was a high energy E plus E minus, and also the electron proton option, high energy, then you have the FCC. So this is 2 years after that, Michael Benedict started the study and CDR and cost review for the next. And you see that this is the same idea of the tunnel. And you have now 100 kilometers with 100 TeV, or 80 kilometers with a higher field for the magnets, but still 100 TeV. This is where we are now. So people should realize what the life cycle of these accelerators are. 1983 was the first preliminary performance estimate for the LHC. Then there was a kickoff meeting. And then 1994, there was the decision to construct. 2008, the first beam, and then the accident. 2009, repair. Start of beam operation, the end of 2009. Very nice performance, 2010 and 11. Discovery of the Higgs boson, July 2012. And as you saw, it used to be 2025, the end of the present LHC program. But in 2012 and now in 2018 and 19, there is now a proposal for a much higher energy collider. And people should realize that this super LHC or FCC, it's of the same order of size as the American superconducting super collider was. It had 81 kilometer circumference, and that was approved for a few years and then was stopped by the Congress, the US Congress. So if this proposal will bring us, from what I saw of Michael, it'll be really about a 100-year adventure. So there was a lot said, and here I try to summarize some of it. This is the last slide. 5 decades or 50 years of Hadron Colliders, is a summary. There's a lot I've missed here, but I put in the things which I think are more relevant for us. J-up psi, discovered in 1976. Very important thing was the stochastic cooling experiment in the ISR of 1974, because this allowed the SPP bar S to be built and the discovery of the W and the Z. Discovery of the top quark at Fermilab in 1995. Discovery of the tau neutrino in 2000 at Fermilab again. And here, this was important. I didn't have time to go through this because it's a very interesting era. The SSC project was here, and there were two DOE reviews, one in 86 and one in 2000. There was the project preparation for the LHC. Here, in, when was it? 1993, the SSC was cancelled by the US Congress because of cost increase. Almost immediately afterwards, the LHC was approved. I don't think LHC would have been approved if the SSC had have continued. Then we did the construction of the SSC, the LHC repair, and into LHC operation. And then we had the discovery of the Higgs. Then we had the FCC proposal in 2012 and the full conceptual design report this year. And we are here. And let's hope that this chart will be extended for another 30 or 40 years. Thank you very much.